Okay, so this is lesson 11, and I just want to recall that last time we introduced this idea of the dot product, and one of the things that the dot product gave us was a way to determine the angle between two vectors given algebraically, and to do that quite easily, so that was good. Another good thing about the dot product was that it allowed us to tell very quickly whether two vectors given algebraically are perpendicular to each other. Okay, and we're going to see that perpendicular vectors are going to be important for us as we move on to do more analytic geometry. Okay, so for now, those are the main applications for which we use the dot product. Today, we're going to see another one. Okay, and I'm actually going to start with something that we'd worked on before. Okay, so if you remember the questions that involved somebody pulling a sled. So, you know, you got a sled on the ground, somebody's pulling with a force at some angle to the ground, and we wanted to determine what was the portion of that force that was in the horizontal direction. So what portion of that force is actually pulling it as it moves horizontally. Okay, then we had another question where you had something, an object on a ramp. So the only force acting on, and of course we were assuming no friction, as we often do in a math course, is the only force acting on is the force due to gravity, but you want to know what component of that force moves in the direction of the ramp, or at least applies to the object in the direction of the ramp. Okay, so there you go. So you might want just the magnitude of that force, or you might want the vector itself. Same thing here, break it up into two perpendicular components, and you want to know what portion of that force is in the direction of the ramp. All right, so the first thing I want you to think about is, how did we do that? Okay, so I'm going to give you a minute to think about that. Well, okay, so we're back. So who can tell me what information we needed in order to you know, figure out those components of the force? Okay, and then when we talk about components of the force, we are breaking it up into perpendicular portions. Okay, so the hypotenuse. Okay, so in this case here, usually we would be given the force that's being applied. So whether it's something that's given or whether it's something due to gravity pulling it downward. Okay, and we needed some angle in there. So in this case here, it could have been, you know, the angle from the ground. All right, and then here, I believe in that question there, they gave us the angle of the ramp, and we were able to use some geometry to figure out an angle, one of the angles inside the triangle. And then from there, we could determine, because these are right angle triangles, we could just use primary trig ratios to determine what we needed. All right, so here, if it was this one here, presumably, you know, we use something like cosine if you're given the magnitude of that force. All right, now what we want to think about now is, well, what happens when we want to find the component of a force or a vector? Let's not even just limit ourselves to forces here, in any direction. Okay, and in particular, how do we move this up to 3D? All right, because you know, I'm sort of giving away a bit of the issue that's going to come up in number 2, but the idea is, I don't want to have to work with the angle between vectors if I don't have to. So even before we start, we kind of know that this is what we're aiming to do, is we're aiming to solve this problem without having to directly use the angle. Okay, but we're going to give this a different name. We're not going to necessarily call it the component of a vector in a particular direction. It's got its own name. Okay, and just to give you a sense of where this name comes from, well, it kind of makes sense. Okay, I'm gonna get a little bit of darkness here. All right, so I'm gonna try to do this as well as I can. A bit tough when you're doing this. Okay, so let's say this ruler here represents the direction in which I want to determine the component of another vector. Okay, so let's say there's my vector, and I want to determine the component of this vector in that direction. Okay? Well, when you think about it, you want this to drop down so that it hits that vector at 90 degrees, like we were doing before. Okay, so that you create, this component along the ruler, and then you can consider a component that goes up to the tip of the vector. All right, and the way you can think about that is, give me just a second, is you can think about it as the, okay, a bit tough to do with my, let's try to do it this way here. This is, I knew it was going to, hold on, it's just going to be back in a second. All right, let me try to position myself a little better. It's essentially the shadow that's created by the vector in the direction of the of that vector that's represented by the ruler. Okay, so that shadow of the pencil that you're seeing is what we call the projection of this vector onto that vector. Okay, so we don't talk so much about the component of the vector in that direction. We talk about the projection of the vector onto that direction. So if the pencil is vector u and this is vector v, that vector that's formed by the shadow projected by the vector u is what we call the projection of u onto v. All right, now of course this second vector doesn't need to be along the plane. These two vectors can be anywhere in 3D. And so what we do is you just take your, it's all about taking your, it's very hard to get the, well, this is a lot easier in class. Let's see if I can get it. No, I can't seem to get a good one here. What I'm trying to do is I'm trying to create, there we go, that's not too bad. So it doesn't matter where these vectors are, is the projection represents the shadow of the vector onto another vector if I were to place my light directly above. So I'm placing my light here directly above. So that's what we mean by the projection. But essentially, what that represents is what is the component of that vector in the direction of this second vector. All right, so presumably all of this has something to do with this new operation we've just determined. Okay, so let's try to draw this. Sorry, that didn't work out as well as I was hoping it would, but what are you going to do? We make do. Okay, so let's see here. So we talk about, what we want to do is we want to determine the projection of this vector u onto this vector v, or in the direction of this vector v. Okay, but what I want to focus on first is I want to focus on what I'm going to call the numerical component of the vector. Now, numerical component of the vector. Can you tell me what word I didn't use here? That might seem like a, yeah, okay, so I just want you to think here that I purposely did not use the word magnitude. Okay, so as we go along, try to think about why I'm using this word numerical component of this projection. Okay, so I just wanted to point that out, that it's not by accident that I didn't use the word magnitude here. Okay, so let's try to draw a representation on this. So let's say this is the vector that I'm projecting onto. So this would be the vector v, and here's my vector u, okay, that I'm projecting. And again, imagine that I have my light being placed, perpendicular to v above u. It's going to create a shadow, okay, at 90 degrees. And what I'm interested in here is just the numerical component. Okay, so this numerical component is what we call the scalar projection of u onto v. Okay, so this is the notation, and what this represents is, it represents exactly what you would expect: scalar projection of u, so vector u, onto vector v. Okay, So it's very important that this is the vector that you're projecting. This is what you're projecting onto. And what you want to determine is this length here. Okay? So what I want you to think about, again, I'll give you another minute because it should be pretty similar to what we see in the above example. Okay? But what would you have to do? What steps would you follow to determine the length of this shadow that's created onto vector V? Okay, so I'll give you a minute to think about the procedure you would follow. So what would you have to determine first? So remember, you're given the two vectors algebraically. What would you have to determine first? And then from there, how would you determine the length of this shadow? Okay, so we'll be back in about a minute. All right, so who can tell me what information I would need to find before I could start, before I would go ahead and determine this scalar projection? So what are the things I would have to find first? Who'd like to throw out some ideas here?
Angle between the two vectors. Okay,
so the first thing you would want to do is find the angle between the two vectors. Okay, so step number one is find theta. Okay, the angle between u and v. Okay, and what else would you need to actually calculate? Okay, yeah, might as well find the magnitude of u, because this magnitude of u forms one of the sides in the triangle, in this right angle triangle that I took a new eraser, didn't work out so well. All right, so now I have enough information, because if I have a side length and an angle inside a right angle triangle, I can find whatever I like. So I can also find the magnitude of u. Okay, and once I have theta and the magnitude of u, what can I do? What would be the calculation that I actually do? Well, take a look at the triangle, take a look at what I'm looking for. What would I be using? There you go. I would be using cosine. Okay, I would be using that cosine of theta is equal to the adjacent, which is my, here, let's call this x here. Okay, my adjacent side over my hypotenuse. Okay, so that means that x, the scalar projection, excuse me, of u onto v would just be given by magnitude of u times cosine of theta. Okay? So, question is, what's the problem here? You know, these are all things I can do. I can find the angle between two vectors. I can find the magnitude of a vector, and then I can calculate all of this. What's the issue? If there is one, maybe we're just happy with what we have. Yeah, seems like a lot of work. Exactly. This, you know, I mean, is there a way to kind of, you know, everything we've been trying to do here. So first of all, almost always involves never having to work with the angle. That's what I referenced before, is who wants to find the angle? Even though now we have a quick way of finding the angle. I can use the dot product to find the angle. It's not that it's that big a deal. It's certainly better than it was before. But the whole point of working algebraically is to not have to rely on the angles involved with these vectors. So this is where now I'm going to, you know, we'll kind of look at this together and get to number 2, which says we would love to not explicitly use theta. And this is where I want to ask you, does this expression look familiar? And someone did, you know, reference it, but does this expression kind of look familiar? Does it not look like something we've seen, maybe with a little missing component? The magnitude of the angle times the cosine of the angle between them. Yeah, and what does, yeah, it kind of looks a lot like the dot product between the two vectors, okay? Exactly, you're just missing the v. So if I now take this and say, hey, I want to try to work without the angle here, what I already have is that the scalar projection, okay, of u onto v, we know is given by the magnitude of the vector I'm projecting times the cosine of the angle between them. And I could make my life a lot easier by bringing in the dot product, because I know how to find the dot product without having to use the angle. So the magnitude of v is not there. What do we do when there's something that's not there that we would like to be there? There you go. Just put it in. But of course, we have to put it in. We have to put it in legally. So I can't just sort of stick in a times absolute value. A magnitude of v, but I can multiply it and divide it. So what I can do is I can take this expression here and multiply it. Remember, this is just a scalar quantity. So this is the magnitude of v and divided by the magnitude of v. So essentially all I've done is I've multiplied it by 1. And now I can use my properties of numbers and put the magnitude of v wherever I like. And lo and behold, what do we have in the numerator? What does that represent? That expression in the numerator? It just represents the dot product of my two vectors. Okay? And there you have it. Okay? It's a way of determining the projection of one vector onto another, or using the terminology that we had before, the component of a vector in a particular direction, and it doesn't need any of that geometric knowledge that we needed before. In other words, we don't have to work with the angle at all, okay? Because this u dot v contains in it the angle of the vector, okay? So this is pretty nice, all right? Now, one thing I want to make sure that we're clear on here is the order, because if I have u dot v, is that the same as v dot u? Yeah, we know that dot product is commutative, but it's very important to have the correct vector in the denominator, or the magnitude of the vector in the denominator. And it's very important that we see that this vector here is the one we're projecting onto. So this is what we're projecting onto. Okay? So it's a way to try to remind yourself of the correct order here. Now, one of the questions in the homework is going to be, should the projection of u onto v be the same as the projection of v onto u? Now, if you look at this diagram, I'm hoping you're already seeing the answer. In other words, is this a commutative operation or not? And I'm hoping that you're seeing the answer just by looking at this diagram. Okay, but we'll leave that for you to think about in the homework. Okay, because this is essentially an operation between these two vectors. Okay, and as usual, we want to know, is it commutative? All right. So you can imagine that this is an important thing to know. So let's say I've got, some force vector, okay, but something's moving along a ramp in this direction, and you can use a vector to represent the direction of the ramp, that you might want to know what's the component of this force in the direction of the ramp. All right, and what this allows you to do is to determine it completely algebraically without having to know the angle between the vectors or having to determine the angle between the vectors. Okay, now this is where I'm going to give you a minute to think about it, because, like I said, I keep using this word numerical component. This kind of looks like I'm talking about the magnitude of this vector, okay, in that direction, but yet I keep using the term numerical component. And one thing we know is that u dot v, we know magnitude of v is always positive, but u dot v is not always positive, okay? So what I want you to think about is, what does it mean for the scalar projection of one vector on another to be negative? And where you might want to start thinking about that is, what does it tell you about u and v if their dot product is negative? Okay, so I'm going to give you a couple of minutes to think about what it means for this scalar projection to have a negative value. Okay, so I'll be back in 2 minutes, so at exactly 3 o'clock. Okay, so we're back. So just to go back to what we were talking about before, okay, if you look at this definition for the scalar projection that we came up with, the denominator is always positive. So the only way for the scalar projection to be negative is if u dot v is negative. So what does it mean for u dot v to be negative? What does that imply about the two vectors if their dot product is negative? So remember, that would mean that magnitude of u times magnitude of v times cos theta is negative. So what must that tell you if this expression is negative? There you go. The only way for this expression to be negative is if cos theta is negative. And when cos theta is negative, we know that the angle is between 90 and 180 degrees. Okay, so here theta is obtuse. All right, so what does that mean? Well, it means that if this is the vector I'm projecting onto, say v, it means that u must be pointing in the opposite direction. So this scalar projection, this shadow that we're looking for, is in the opposite direction to the vector v. Okay, so that's what it tells us. If this numerical component, if this scalar projection is negative, it means that the angle between u and v is greater than 90 degrees, and it's going to create that shadow on the other side of v. Okay, useful information to know. Okay, so up until now, any questions before I move on to page 2? Anything we want to ask about anything we've produced at this point? So we started off with a very geometric viewpoint, but in going through the steps, we realized that we could replace something that required geometric knowledge, like the angle between the vectors, by using this operation, which does not require the angle between the vectors. Okay, so any questions? No? Okay. So essentially what we've determined here is, because we've been focusing on the numerical component, essentially what we've been determining is the magnitude of the projection vector. Okay. However, we have to be careful because it's not really a magnitude, because it could also be negative. But what does that negative tell us? Well, the absolute value of that number would still give us the magnitude of the vector, and the negative just tells us that it's going to be in the opposite direction. Okay? But what we want to look at here is, how do we find the actual vector? Okay? So now, okay, so it's important that you're clear on the notation. Is if I get rid of the word scalar, okay, and I just say projection of u onto the vector v, this is what we call the vector projection of u onto v. Okay, so this here is a vector quantity. Okay, so it's essentially what I drew here. Okay, this represents the vector projection. Okay, the scalar projection just gives me that numerical quantity, which represents the magnitude if the angle between them is less than 90 degrees, And if the angle is greater than 90 degrees, then it's sort of the magnitude, but the negative tells you that it's pointing in the other direction. Okay? So when you think about it, we already have the magnitude component of this vector figured out. Okay? What we need to do is figure out how to turn that into a vector. So let's go back to our diagram again. Okay. So again, say I'm projecting U onto V, except now what I'm looking for is this vector. Okay. Well, I already know the magnitude of this vector. The magnitude of this vector, okay, and let's just take this version here where theta is less than 90 degrees. I already know that that's given by U dot V over magnitude of V. Okay, so I've already got the magnitude portion covered. What I need is a way to represent the direction of this vector. Okay, so this is where I want you to think now. I want you to think, what do we have that would give us the same direction as vector V, but in a sense would not contribute to the magnitude of vector V? Okay, there you go. You realize that, wait a minute, what if I took the vector that's in the same direction as V, but magnitude 1? Okay, so in other words, as a couple of people have said, let's use good old V hat. So the vector that's in the same direction as V, but with magnitude 1, then if I find this scalar projection to be equal to 7, then all I have to do is multiply 7 times this vector, and I get exactly the vector I like. Okay, if the scalar projection we found to be 14, well, just take this vector magnitude 1 multiplied by 14, we get the vector of magnitude 14. And what if this scalar projection is negative 3? What's it going to do to my vector? Well, not only am I making it 3 times longer, I'm also pointing it in the opposite direction, because that's what a negative does to a vector, is it just points you in the other direction. And so this is where we realize that we have a very nice way to take this quantity, which we've already determined a nice easy formula for, and then incorporate the direction that we're interested in by using the good old unit vector. So if you remember in the past, I said, these unit vectors are going to come in handy for us. So if we're looking for what we call the vector projection of U onto V, what we do is we take the scalar projection, and we just multiply it by the unit vector in the direction of V. And of course, how do we find the unit vector in the direction of V? Whoops, sorry, I'm talking, and that was a very dumb thing I just wrote. Please strike that from the records. Okay, of course, how do we find the unit vector in the same direction as V? Is you take the vector and you divide it by its magnitude. Okay, sorry, I don't know what I was thinking there. Okay, so this portion represents that numerical component, okay, which has the magnitude, and if it's negative, also tells you that it's pointing in the opposite direction, and this contains the direction component of your vector. And you can clean this up a bit. Very often we write it as U dot V over magnitude of V squared times the vector V. So this is a scalar multiplication. Okay, is we're taking this value here and multiplying it to vector V. And obviously if this, if it's negative, then the projection points in the other direction. Okay, and this is a nice application of the dot product, because we're taking something that is very geometric in nature, and we are representing it by this nice algebraic process, which doesn't involve us ever having to know what the angle between the vectors is. Okay? So, scalar projection, I need to see the word scalar. You'll notice the textbook kind of writes out a sentence to represent the scalar projection. There's different notation for projections and scalar projections. This is the one I like, so this is the one I'm going to use. The textbook, though, does use, I think, a slightly different notation for this here. All right? So I'm looking at the time, and what I would say is I'm going to leave number 6 for now. If we have time before 3:30 to come back to it, because it's something we've already done in the past. You notice here it has to do with finding direction cosines, which we've already done. This is just another way to get to that. Okay, so if we have time, we'll come back to it. But I think what we'll do, because I do want to introduce something before we leave, is let's go and solve this problem, which, okay, you draw yourself a little diagram to help you out, but in the end, you should be solving this purely algebraically, okay? And you notice here, all the information is given in terms of algebraic vectors, okay? We don't ever talk about the magnitude or the direction explicitly, okay? So I'm gonna leave you to work on number 7. It shouldn't take too long, so I'll leave you like maximum 2 minutes. So at 3:13, I'll come back. Okay, so we're back. Let's take a quick look at this here. Now, again, I'm not even going to make any effort to draw, even though this is in 2D, I'm not going to make any effort to draw myself a diagram that's accurate. Probably don't even need a diagram, but I would like to just think about how this works. So say this is what I'm projecting onto. So that's the vector 5, 2. And say here I've got the vector 4, 3. This is the force that I'm projecting on to this direction. Okay, so if I'm looking for that numerical component of the force, okay, in the direction of motion, all right, and in particular, I'm interested in the magnitude of this force, okay, well, let's take a look here. I'm going to take my scalar projection of vector 4, 3 onto vector 5, 2. Now, since I'm only interested in the magnitude, is there something I should be adding here, since I'm only interested in the magnitude of this force? Well, what type of value can this have and that have? What do I have to be careful of here? There you go. Is that here, since I'm only interested in the magnitude of this force, okay, they're not specifically asking me for the direction, okay, then I really should be taking the absolute value of that, okay, if it turns out to be negative. So now, again, nothing to do with that. I'm not even going to draw an angle on here. Couldn't care less. I guess I could draw this thing here to represent my my scalar projection. But essentially, all I'm doing, since it's scalar projection, is I'm doing u dot v. So 4, 3 dot 5, 2 divided by, and I'm dividing by what I'm projecting onto, which is v. So the magnitude of 5, 2. Okay, and there we go. What do we have? We have 4 times 5 is 20 plus 6, so 26. So it's in the same direction. And then here, square root of 25 plus 4. So we have 26 over square root of 29 newtons. Okay, and there you go. Now, if I wanted to find the actual, you know, this is not what's being asked for, but we might as well answer this question. If I wanted to find the force in the direction of motion, what would I do with this number here? So I now know the magnitude of this vector. What would I do now if I wanted to determine the actual force vector in that direction? There you go. Multiply by that unit vector. Okay, so I'd just be multiplying 26 over root 29 times the unit vector in the direction of that motion. So what do we have? We have 5, 2 divided by, well, we already found that magnitude. That's root 29. And of course, what happens when I multiply root 29 times root 29, I just get 29. So I would just end up with 26 over 29 times 5 and 26 over 29 times 2. And I guess I could calculate that. What would it be? This would be 100. So it looks like 130 over 29. And this would be 52 over 29, I believe, if I didn't make any silly mistakes. Okay, so this would be just the magnitude. This would be the actual force. Okay, where I take my scalar projection and I multiply it by the unit vector in the direction I'm interested in. Okay, and obviously if this had turned out to be negative, then it would have meant that the force was actually in the opposite direction. All right. So any questions on this here? All right, so I'm going to move on to that other little thing. So I think maybe what I'll do is I'll leave this. The solutions are going to be posted if you want to look. It's pretty straightforward. Essentially, you know, remember how we define those direction cosines. Okay, I think I was supposed to change this to make it the z-axis just to make it a little nicer. Okay, but the idea here is if I've got some vector in 3D, okay, and I want to determine the angle to the x-axis, okay, I realize that this x component is just going to be the projection of the vector onto the x-axis, okay? It's like if I take my light above that vector and I project it onto the x-axis, the shadow it creates is just going to be the component. And you can use this idea to solve the problem. And guess what you're going to end up with in doing all of this? The exact formula we determined for the direction cosine to the x-axis, okay? And it's very similar to the y and z-axis. So I'll leave it. If you have time to look at it, you can. But otherwise, I want to get to something that you'll see on the in the worksheet, but you won't see in the solutions because it's more just it's an introduction to what we're going to be looking at a little later on. Okay, so what I want you to do is I want you to think about, you know, this this wrench here. Okay, and what do we do with a wrench? Well, we apply a force, say in this direction, and we make the wrench turn, and of course it makes the screw turn. Or I could apply a force in that direction and move it that way. And what's this righty-tighty, lefty-loosey rule? What am I talking about? By the way, this might end up being the most useful thing you learn from this course in the rest of your life. So what does that mean, righty-tighty, lefty-loosey?
If you want to tighten a screw, you move the wrench to the right, and then if you want to loosen it, you move it to the left.
There you go. So now I know for sure that Charlie at some point has done some fix-it at home or built something, okay? Because he realized that if I want to tighten something, I got to move it to the right, okay? And I tighten it, and then when I want to when I want to unscrew it, I have to move it towards the left, and that unscrews it. You know, by the way, like I said, you'd be surprised when you're in a panic and you suddenly have a leak in the house and you have to turn your faucet. You actually need to think in what direction. So think righty-tighty, right closes it, left loosens it up. Okay. So here you got a ratchet, very similar to this scenario here where you've got a wrench. Okay. Now, what I want us to think about here is let's take a look at what I'm doing. So let me bring this up a little. Okay. So say here's the thing that I'm trying to screw in or unscrew. Okay. So I apply a force. Okay. So here's my handle, which is going in this direction. And then I'm applying a force like this, and I'm turning it. Okay. But what motion is produced beyond just me moving the ratchet towards the right? What other motion is going to be produced as I do this?
The screw is going to rotate.
The screw is going to rotate, but yes, what else? There's something else, there's another motion that's going to be produced. There you go. Is the screw is going to be going into, in this case here, the wood, or say here downwards. Whereas if I move to the left, okay, yes, it's going to produce this rotational motion, but it's also going to produce a motion, the screw coming out of the wood or going upwards. Okay. And what's interesting about that, say we represent it by a vector, is look at our ratchet here. Okay. And then I apply my force. Okay. These two things are on the same plane, but what is special about the direction that is being produced when I apply to this vector here a force in this direction and it's producing a motion downward? What is the relationship between that motion downward and these other two vectors? Okay. So you're talking about the motion. So that is correct. But what I want to think about is I want you to think about the length, the handle of the ratchet as being a vector, the force that I apply to it as being another vector, and then it produces a motion downwards or straight upwards. There's a relationship between this vector going down and these other two vectors. Yeah, we're definitely creating in 3D. Notice that the motion that's produced downwards is perpendicular to both of these two vectors. Okay? These two don't have to be perpendicular, because I could apply the force this way. I could also apply the force that way so that the angle between them is not 90 degrees. But the motion that's produced going directly down is perpendicular to the other two vectors. Okay? So where is this taking us? Okay? It's taking us to needing a new operation. Why do we need this new operation? Okay, so again, can't make it contradict anything. We need this operation because it's useful. Okay, that's why we're even looking for such an operation. Is what I'm trying to do is I'm trying to find an operation between two vectors. As an example, the vector along the ratchet and the force vector. And I'm looking to find a way to determine a vector that's perpendicular to both of those vectors. And that's going to take us to a new operation, which we're going to look at on Thursday. Okay? And guess what? That's going to be our other multiplication. So we have that one I guess our third multiplication. We have scalar multiplication, which is just about taking a vector and making it longer or shorter or changing direction. We have dot product, which is useful in determining the angle between two vectors. Now we're going to need a third multiplication that's going to produce. Yeah, I know Kieran keeps giving us those spoilers. I'm not quite sure why he does that. Okay, and then we need another operation that's going to take two vectors and produce a third vector that's perpendicular to those two. Okay, so that's where we're headed on Thursday. And we're going to see that this operation is going to be very useful physics-wise. Okay, in fact, you've already seen, I'm sure you've already seen one of the applications, but we're going to use it in a more mathematical way as we move on to doing our analytic geometry in 3D. Okay, we're going to see how this new operation is going to be very useful. Okay, so that's the end of this lesson here.